In this video, I'll talk about the reduction of carboxylic acids and its derivatives to alcohols and sometimes only to aldehyde depending on what type of reducing agents you're going to be using. So far, we know the reducing agents that we have used is the NABH4. NABH4 is not that commonly used in case of carboxylic acid and derivatives, but possibly can be used with acid halides, because acid halides are actually more reactive than the aldehydes and ketones. So you can technically use NABH4 with acid halides, but for the rest of them, you can't really use them. So I can say that the most common reducing agents that you're going to be seeing here is going to be the LiAlH4. Because remember, this one is a stronger reducing agent. And when I'm looking at the NABH4, it's in a mild reducing agent. And I'll kind of summarize the differences, like what they can reduce at the end of this video. But right now, I'm going to focus more on the LiLH4, so because it's in a stronger reducing agent. Now, in addition to LiLH4, so where we have 4 hydrogens, you can do a little bit of manipulations with the number of hydrogens and get something else, like I can have possibly LiAlH, and I'll have R3 basically, or 3 of the R groups. So you can just say R3. So most common R groups that's typically used in that case is the isobutyl groups. So I can use something like LiAl, or I can probably just write it down this way. I'll write down CH3 to CH2. I'll use 3 of them, and I'll have ALH. So only one hydrogen at the end of the day. So I don't think you have to worry too much about memorizing like what particular R group that you really use, but rather know that the difference is when you're manipulating going from. And a typical LiLH4 is you can reduce the number of hydrogens to make this less reactive. It's not going to be as strong a reducing agent anymore. And sometimes it can be a little bit more selective with what it can possibly react with. Now, this particular one is typically called a DIBAL. So you probably wouldn't even see something like that, but most likely you would see DIBAL-H written down, and that's when you see something like that, that means we're talking about this particular manipulation of the reducing agent. Now, this one is most commonly used to reduce esters to aldehydes. Okay, now another one that I got in line here is I can have an OR group, so I can have Li OR3 ALH. So this one doesn't really have any specific name, but an R group could be anything. Most of the time you use an butoxide here. But again, what we're really doing here, we're reducing the number of hydrogens, so having an oxygen there makes a difference. So it's not going to be as reactive anymore. So it's very less reactive. And this actually is used to reduce acid halides, especially acid chloride, to aldehydes. So it's not as reactive, so it doesn't really go all the way to an alcohols. Typically, you would see a lot of these reductions using LiLH4 going all the way to an alcohols and sometimes to an amine, depending on what functional group that we're talking about. It does go through the formation of aldehyde, but I can't really stop it in an aldehyde because the LiLH4 is a very strong reducing agent and it reduces the aldehydes back to an alcohol. So even though a lot of these reductions may go through an aldehyde, but you can't really just stop it, and as a result, it will go ahead and get to the next one in line. And a typical common, like I wouldn't say the mechanism is going to be the same for every single one of those, but the most common mechanism kind of looks like this, where I have, suppose, some sort of a leaving group is in a Z here, and that could pertains to like OR or like an anhydride or even like chloride. And the OH probably works a little bit different. That's because the OH is also an acid along with being in a leaving group. And a lot of times when we're using these LiLH4, it does have potential to act as a base as well because it's in a strong reducing agent. So what I'm really getting out of here is obviously the hydride here, so the H minus technically, and that H minus is going to go ahead and do the attack here, and then this comes out. So what I get as a tetrahedral intermediate, and you can go back to looking at the generic reaction that we have talked about when it makes a tetrahedral intermediate here. You got one of the hydrogens installed here. Now I know this actually has a leaving group, and that's going to happen to most of these things. That since it's got a leaving group, I can reform the pi bond, and then this can get knocked out. So what I get, I made the pi bond again. I got one hydrogen installed. So this more looks like an aldehyde at this point. And then I can't really stop it here. As a result, the second molecule of hydride or second set of hydride kind of comes in here, and it would do the same thing. It will do the attack here, and then this comes out, and you ended up getting a tetrahedral intermediate again, but this time it does not have any leaving group. So let me just go ahead and keep track of colors there. Minus. I got the hydrogen here, got the hydrogen, second hydrogen here. So I can't really do anything at this point. I'll just do the acid workup. And typically the second step, so you might be using like excess of lithium aluminum hydride here, at least two equivalent. In case of an acid, you might be using actually three equivalents because the first equivalent would be used to deprotonate that. I'm not going to be talking about their individual mechanisms, but just this is how generically it's going to look like, where you are going through an aldehyde, but you can't really stop it in an aldehyde unless you use something like DIBAL in case of esters and use this LiOR 3ALH in case of an acid halide. That's when you can stop it at an aldehyde. Those are selective, but the rest of the times it would go to an alcohols, and in case of an amide, it'll go to an amine. So, for example, here, if I run this reaction with, I would say LiLH4, and I'm going to be using an excess, at least three equivalent, and then we'll just do acid workup at the end of the day. So when I'm doing this acid workup at the end of the day, I'll end up getting an alcohol here. It will go through the formation of an aldehyde, but you can't stop it, so it will go all the way to an alcohol. So that's what you want to make sure you know. And I can probably just say the same thing would happen with this guy here. I would not be using, like here I said I need to use at least three equivalent. In case of an acid halide and even anhydride, well, acid halides especially, I would be using two equivalents at least. Because I don't have to worry about using one of the equivalents of aluminum lithium aluminum hydride here to deprotonating that hydrogen like we were doing in case of an acid, because this is not an acid. So I can easily go ahead and use the first equivalence just exactly how we have done up here. The first equivalent will go ahead and attack this carbonyl carbon, makes this tetrahedral intermediate, and in this case of Z, you would have a chlorine here or an X here, any other halogen possibly, and then you reform the pi bond, halogen leaves, makes the aldehyde, and then you redo the attack with an hydride again. So ended up making it an alcohol. So makes it an alcohol here. I can say something similar. This might actually needs a lot more because you have technically two sides that kind of got the carbonyl. So I would use an excess of aluminum hydride here, and then obviously the acid workup at the end of the day. Sometimes you may just use water. Like you don't have to have a strong acid. Sometimes just the water do the job just fine because you're just trying to protonate the O minus in case of this to make it an alcohol. So here I would make this as one type of an alcohol. And if my R groups are different on both sides, then I'll make another type of alcohol. But if R groups are the same, then it would end up making the same type of alcohols from both sides when you're reducing them. When you do the esters, on the other hand, kind of in the same story, it works very similar to what we're doing with the acid halides up there. So I would have at least two equivalent of LiLH4 and then H3O plus work up. And in this case, again, if those R groups are different, then I'll ended up making two types of alcohols. That's one type of alcohol, and this would have been your other type of alcohol. In amides, using LiLH4 again, excess with just water in this case. You probably don't even need an acid here. Just to work up, I'll end up making an amine. So I don't make it an alcohol, but rather I'm making an amine. So that's something you want to make sure you keep in mind. In case of a nitrile, same story. We use excess AlLH4, at least two equivalents. You got water, and it ends up making an amine again. So that's really the difference. Like sometimes you make amines, sometimes you make alcohols, depending on what function group you're really starting out with. But this is really the overall pictures of these um, carboxylic acids and derivatives going back to an aldehydes and ketones. So remember what I was saying earlier here. So if I was using this LiLH4 with acid halide, and even with the esters here, it does go through the formation of an aldehyde, but I can't stop it at an aldehyde, so eventually it will makes the alcohol. So then the question is there a way where we can stop the reduction at an aldehyde? And the answer is yes. And the answer lies to using an DIBAL in case of an esters and using this LiOR3ALH in case of an acid halide. So they're typically kind of very selective to those two guys. So that's why it kind of works really, really good with those particular function groups. So make sure you know that. So if I want to go ahead and summarize this, so I have LiLH4 where I can have that can reduce a lot of things. They can reduce aldehyde, ketone, acid, acid halide, esters, and hydrides. So all these right there, they get converted to an alcohol, all the way to an alcohol. Amides and nitriles, they get converted to an amine using LiLH4. The NABH4 is typically used to reduce aldehydes and ketones to an alcohol because it's not a strong reducing agent. I'm going to go ahead and add acid halides as well, even though it's not commonly seen in the books, but it can still reduce the acid halides because remember, acid halides, it's even more reactive than the aldehydes and ketones. So I can technically use NABH4 with to reduce an acid halide, and that would actually go all the way to an alcohol as well. Even though it will go through the formation of an aldehyde, but it will go reduce the formed aldehyde back to an alcohol. Now, if you want to be selective, I can use acid halides, typically acid chloride. Using this LiLHOR3, I would stop this reduction at an aldehyde. And if I'm using an ester, I want to use DIBAL, and that would stop this reduction at an aldehyde again. So it's not going to take it all the way back to an alcohol.